All right, welcome, ladies and gentlemen, to Lesson 2 from Unit 3. This is going to be kind of a big introduction to all of our derivatives. So we're going to be looking at the derivative of a function using the definition. All right, so in the previous lesson, we learned the definition to find the slope of a tangent line at any point A. And what we're going to do today is we're going to figure out how to find the actual derivative. So it's like the slope of the tangent line at every single point x. Whatever x you want to use, you can plug it in afterwards. So the definition is here. This looks exactly like, or almost exactly like, the one that we used in the previous lesson, except for in this case, you notice we have this f prime of x. This is our big definition of the derivative. The limit as h approaches 0 of f of x plus h minus f of x all over h. You notice it looks exactly like the other, except for we have an x in place of the a. And this is kind of how it's said. The derivative of a function f with respect to the variable x. That means that's what you're taking the derivative with. As the function, or is the function f prime whose value at x is given by this statement. That's if the limit exists. Sometimes it doesn't work, and then sometimes you can't find the derivative. But if a function is differentiable, which means you can take the derivative of it, at every single point on its domain, it's called a differentiable function. So let's take a look at an example. We're going to differentiate f of x. In this case, it's x cubed. So we're going to take f prime of x. So you got to remember that the word differentiate means take the derivative. And we're going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. So we go ahead and do this. We say the limit as h approaches 0 of x plus h cubed. If you remember binomial theorem, or if you remember your Pascal's triangle, this comes out to x cubed plus 3x squared h plus 3xh squared plus h cubed minus f of x. Well, that's just x cubed. Or all over h. All right, we need to go ahead and simplify a few things here. Combine any like terms. Well, it just so happens I have an x cubed and a minus x cubed, so that goes away. 3x squared h plus 3xh squared plus h cubed all over h. You'll notice that I can cancel my h's because that's the whole key to this formula, if you want to call it a formula. The h is canceled, so I get 3x squared plus 3xh plus h squared. And that's all to the limit there. All right, so now I need to evaluate the limit. Since h is no longer in the denominator, I can just go ahead and substitute. That goes to 0. That goes to 0. Because the limit as h approaches 0, that means those two products become 0. And I'm left with 3x squared. Now, that is the derivative, by the way. That is f prime of x is equal to 3x squared. So 3x squared is the derivative of x cubed. But we could go farther and asking this question. I could ask, hey, what is f prime of 2? Well, then rather than doing the whole definition of the derivative thing again with 2 in there, I know the derivative is 3x squared. So that means I can just do 3 times 2 squared. Sorry for the choppiness there. And I get 4 times 3 is 12. That means the slope of the tangent line at x equals 2 is 12. All right, so that's using the most commonly used definition of the derivative. Now, there's a second one that I need you to be familiar with, but probably won't use quite as often, except for maybe on an AP test where they might ask you a question about it. This is the alternate definition. And you could use f of x, whatever you want to use here, but this is derivative at a point in this case. But it's another version, like I said, it could show up on an AP exam because you need to know what this is going to say. So if I wanted to find the derivative of the function at any point x equals a, I can do that by using this alternate definition, but it's actually kind of a straightforward one. If we were to think about some point, I don't know, x right here, as x gets closer and closer to a, sorry, I wrote the wrong picture there, but what we're trying to do is just finding the slope, and the two x values, these two x values are getting closer and closer and closer to each other. And we can do this by using this formula. Let's go ahead and look at an example here. If I took if I want to differentiate square root of x using this new derivative, or this new quote-unquote new alternate derivative, I want to find f prime at a, but I want to use this new definition. So the limit as x approaches a of f of x minus f of a all over x minus a. You notice this is just change in y over change in x, so still slope again. Oops, x approaching a. F of x is just the square root of x, and f of a is just the square root of a all over x minus a. Well, that's kind of a simple formula, but now we've got to figure out how to simplify this. And we need to simplify this, if you recall from last year, might be hazy memory, we need to multiply by the conjugate here. And if you multiply by the conjugate, really good things tend to happen. So I get the limit as x approaches a of, okay, well, the whole point of multiplying by the conjugate is to get rid of those radicals. So it becomes x minus a all over x minus a times radical x plus radical a. And we need to simplify. Well, here I get x minus a over x minus a. Well, that's good. Now I get limit as x approaches a of 1 over the square root of x plus the square root of a. And if I was to look at this limit, I need to evaluate the limit now. I can take the a, by plugging in a for x, that doesn't affect or make a bad number in the denominator. So this is just going to be 1 over square root of a plus the square root of a, which becomes 1 over the square root, 1 over 2 times the square root of a. And there we get our answer. This is the derivative of the square root of x. It is 1 over 2x, I guess, in this case, because we could say, well, what's the f prime of x? Well, that's just 1 over 2 radical x. Now, the alternate definition is not one that gets commonly used, but like I mentioned, they could probably show something like this on the AP exam, and you need to know that this is also the definition of the derivative. Change in y over change in x still. All right, let's go ahead and move forward. Let's look at our notation. So we've seen f prime of x. There are other notations that get used throughout calculus. The first being this, the y prime. So y prime, if I was to give you, let's say y equals 3x minus 1, and I said, hey, find y prime. Well, that just means find the derivative. It's a nice, simple notation, but the only problem is it doesn't tell you what you're taking the derivative with respect to. Now, normally we understand that it's taking with respect to x, which we should understand. That if I took the derivative of the y prime, I have to take the derivative of 3x minus 1. There are others. Let's keep on this. I'm going to go a little bit farther here first. Oops, where did my thing go? All right, I'm just going to put them all 4 up there because my thing didn't come up when it's supposed to. So under y prime, we get dy dx, and you just read it like that. This says the derivative of y, so this is the derivative of y with respect to x. So this tells us both variables and uses the letter d for derivative, basically. So dy dx means take the derivative of the function y with respect to x. We could write it as df dx, or derivative of the function f with respect to x. Or we can write it like this, all different ways to write the idea of the derivative. D dx of f of x says derivative of f at x. And this one's kind of a nice one because it, like I said, like this says here, it emphasizes the idea that differentiation is an operation performed on f. You take the derivative, just like you would take the square root. Now, this does go a little bit farther. I'm probably jumping the gun a little bit too much, but we can take the derivative of derivatives, and we'll get to this a little bit later, but we can change these symbols a little bit to show that we're taking a derivative and a derivative again. I'm not going to jump the gun too much on that. I'll explain that as we get to it. Basically, what this page is for is so you understand when these symbols show up, you know what we're trying to calculate. Okay, one of the rather large things that we do in calculus with derivatives is we take the graph of some function and we attempt to draw the graph of its derivative, or vice versa, take the derivative graph and try to graph the original. And this is also one of those AP exam questions where you're going to be given a graph of one of the functions and you need to determine which of the multiple choice questions is the derivative or the antiderivative. We'll get to antiderivative later. What you have to remember is that f prime means the slope of the tangent line at every point on the original function. So if I was to give you some function, let's draw a function here, and we're going to call this function f. So this is function f, and we want to find the derivative eventually. And this just kind of went like this and like this. Whoops, where's it going? Come on now. Don't mess with me. All right, let's try that again. We're going to draw some function that looks like this. This is called my f function, and we want to try to graph, and we're just going to do our best here. And we're going to do our best, try to draw the graph of f prime. Now, there are some key points that we can look for. First of all, are this max and this minimum point. We need to know that the slope of a tangent line at a maximum and a minimum point are 0. And you should have noticed that on the last lesson that we did. You were asked a few questions, 1 or 2 questions about this. So let's call this a 2, and let's call this a, let's go 5. So 1, 2, 3, 4, 5. So that means at x equals 2, my slope is 0. That means f prime is 0 at x equals 2. And if we go to x equals 5, it's the same idea. So now we already have 2 points that we can use, or that we're going to use to help me graph, or help us graph f prime. Now, in this particular case, we're going to get really bad numbers, but let's just say, or not really bad numbers, but nothing exact. Let's just say right here at like x equals 1, my slope looks pretty steep. Let's call it a 4, which means right here m is 4. So the slope is 4 at x equals 1. We're just going to say it. Okay, the slope is 4 at x equals 1. And at x equals 0, it looks even steeper to me. So we'll say it's just a little bit steeper at x equals 0. And then somewhere in between 1 and 2, right in here, the slope looks like it's probably about a 1. So we can say it's right about 1 right in here. Now you'll notice these 3 points are above the x-axis, which means they are positive. And you notice this side of the graph from over here to and this direction that we can see, the slope is positive. It's greater than 0. If you look between 2 and 5, the slope is negative all the way down to 0. So that means the slope is less than 0, which means on the derivative function, it's going to be below the x-axis down here. You notice it starts off at about 1, gets steeper, and then shallows off back to about 0. So that means it comes down here. If we started to graph this randomly, as it goes down below, it gets steeper, so we just get more negative, and more negative, and more negative, and then it starts coming back towards 0, and then it becomes positive. Small positive, bigger positive, bigger positive, bigger positive. So that means it's going to be small positive, bigger, 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 bigger. Something along this line. And this might look a little bit familiar. If you remember the problem we did a few minutes ago, we took the derivative of x cubed, and we got a quadratic. And notice that this looks like a cubic, and this looks like it could be a quadratic. And that should make sense. But we can go the other direction as well. Let's say I wanted to draw the graph of f given the graph of f prime. Now, don't think you're going to get this stuff right away. This is a pretty complex piece. People have lots of problems with this along the way, but the more you practice, the better you're going to get. So let's say this is f prime. Let's take this line here, and let's say that that's at x equals 1. Oh, let's try that again. I'm going to change this picture. Sorry, my fault. Not paying attention to myself. But let's still use the value 1. All right, so we are going to come in here. This is where I wanted to go. All right, this is the graph of f prime. And we want to graph f of x. Or a possible graph of f of x. You're not always going to get the exact graph, but you could get something that is close. So you notice something happens at x equals 1. The slope changes from -2. So you got to remember that this means the slope is -2. And then on the right-hand side, the slope is +1. So if we were to just choose some starting point here, let's just start here at 1. And on the left side of x equals 1, the slope has to be -2. So we're going to go down to right 1. And there we have the slope of -2. So the slope is -2 there. And then on the other side, the slope is +1. So we're going to go up 1, right 1. And up 1, right 1, and just keep going like this. And there you have, actually, if we were to go ahead and fill this dot in, I'll explain that in the next lesson about that little point right there. But you might notice that there is no closed dot here, which means there was no slope at x equals 1. And that kind of jumps us into the next lesson that that little point means you can't find the derivative. But we'll get to that later. So here f prime tells me the slope is -2 and the slope is 1 on either side of 1. So we just draw in the slope of -2 and the slope of +1. And there you have a version of what the derivative or what the original function could look like. All right, last thing I'm going to leave you guys with is something called a one-sided derivative. A function y equals f of x is differentiable on a closed interval a to b if it has a derivative at every interior point of the interval and if the derivative exists at the endpoint. What we can do is we can take right and left-handed derivatives, or sorry, limits to check the endpoints to show that it is differentiable on a closed interval. Normally we do these things on open intervals, which means it's derivative, or we can find the derivative everywhere. But what this is really going to help us do is find whether or not there's a derivative at interesting points. Like if I gave you y equals the function x squared and 2x when x is less than or equal to 0 and x is greater than 0. We can use left-hand and right-hand limits to show that there's no derivative at x equals 0 because the derivative has to be the same value, or the limits have to be the same value. And if we took the limit from the left on x squared and the limit from the right on 2x, we would find that the derivatives are not the same. I can tell you right now the derivative for the left side, the left-hand derivative for x squared would be 0, and the derivative on the right side for 2x would be 2. We notice that those two values are not the same, and therefore there is no derivative at x equals 0. And that's one thing we can do to show whether or not a function has a derivative at a certain point. And this comes down to a lot of the piecewise functions that we can take the derivatives of. Okay, I'm going to leave you with this. Your assignment is on the Google Docs that I shared with all of you. I hope this stuff made sense, and I hope you guys start your practicing, and I will see you guys Wednesday, it looks like.